celestial mechanics. It was supposed to generate a memoir on this, and there was a competition. It was more or less designed for Poincaré to win. He did win. And there was a prize money and a paper to be published in Acta Mathematica. So the story is that he gets the prize money, he gets the paper published, and he finds a mistake in the proof, at some advanced stage. So he is forced to use all the prize money and more to get back and buy back the issues of Acta. And so he didn't get money from this story, but he realized that he had made some advance. It was not all wrong. He realized a mistake, and we got understanding. So he discovered something. So what he discovered was more or less the following. So the pictures, I cannot draw all the dimensions. If you think about how many dimensions are involved on a three-body problem, it's very far from what I can draw. But you think that you had a picture like this. So this was a flow. So the trajectory was just moving. I just increase one little bit the complexity, which is not the dimension, but this will now correspond to what's called the Poincaré section. I replace this dynamics by a perturbation, not in higher dimension, but in time. So now this will be replaced by a discrete dynamical system. So now the trajectory by this, we imagine that you have the time one map, not just a continuous time, but it just jumps from time to time. And now the iteration follows a discrete trajectory, but you start with the same equations. Now, suppose that you have this and just make a little perturbation. Okay, so consider the situation. And then what happens here? So here there is some kind of circles that are doing. I don't know exactly what is going to happen. I'm more concerned with what's happening here. So what happened here is that when I had a flow, it was more or less, there was this closed curve here. But if you think how this curve is being defined, in the past of this curve is defined by orbits that emanate from an unstable equilibrium. And this part is by orbits that arrive at a stable equilibrium. And somehow when you had a flow, they are forced to match, right? But if it's just a discrete dynamical system, they can just touch. So there may be some orbit here. It's just a tiny perturbation. So there is an orbit that's called the nomoclinic orbit that in the past, it emanates from this. In the future, it goes there. But it's not clear that there will be a curve here. So what could be happening is that the curve made by the past goes here, and the curve that is defined by the future is here. They cross at this point, but doesn't necessarily align completely. So the mistake of Poincaré is more or less that he thought that they had under the equations it was going to force because some power series was kind of trivial, but things are not analytic and things like this. Doesn't matter. So what's the consequence of this? So this he cared about. So if you have this, the whole picture has to be invariant by the dynamics. So there is a crossing. It's forced to cross again. It has to happen because the drawings have to be invariant by dynamics. And it has to cross again. And embedded drawing, but let's imagine that it crosses and crosses. And there is a problem because as it approaches here, so the crossings have to accumulate here because that's where the dynamics is going. But as it approximates, it gets stretched by this. So what actually happens, I forget this curve, is that it has to kind of increase the oscillations as you iterate. So there's a picture like this, where as it approaches the crossings to the unstable equilibrium, it gets stretched in the other direction. And it starts accumulating on the previous picture that you had, and it will kind of accumulate back on itself. So it will create a crossing of second order there, which will create more complications in the picture. I already gave up drawing here. Poincaré gave up drawing there. So he wrote, there is a famous sentence that he says, that this picture that I didn't try to draw, and he says more or less the same, is conveys the difficulties of these three-body problems and other problems in classical mechanics and so on. So just trying to see this picture, he understood enough to see that it was really a new thing, and this defeats the possibility to kind of giving an understanding of the three-body problem, which would have a picture that's integrable. In particular, anything close to integrable, because integrable is orderly, and Poincaré had just discovered chaos. So discovered things that were extremely unstable and in a kind of persistent. So that's what happened with Poincaré. And then let's jump. I don't have there Birkhoff. There's let's go to next guy. So now Smale. So Smale was interested in many things. So initially on topology, and in doing topology, he proved the Poincaré conjectures in the higher dimensions, so dimension bigger or equal than 5. And to do this, he considered, so there was he proved the H-cobordism theorem. So there is a manifold, and then there is a Morse function, and then there are things like this. There are singularities for the most critical points. And then they use this to make the composition of the manifold. So the manifold maybe had a bottom, and then maybe there was a top, and there was also something in between. This is the typical picture of a cobordism. There is a condition to make. So I don't discuss this topology, so he was interested in pictures like that. And there was a Morse function. Another thing that you can do with Morse functions is to consider the gradient flow, and the gradient flow for a Morse function is just a little bit stupid. It just goes up. It does some silly things about this. So this is the dynamical system, but it kind of moves up. And when it meets the singularity, it does something a little bit complicated, but otherwise things are trying to go from here to there. If there are no singularities, you kind of find an equivalence between bottom and up. That's how you prove that two things are homeomorphic at some point. He has to eliminate the singularities. Anyway, there is this kind of gradient flow that he has interest, very trivial dynamical systems. In the last case that his interest, there are no singularities, just a complete thing that moves from bottom to top. Trivial kind of dynamics, but he got interested in dynamics. And being a very overly confident guy, for good reasons, but still overly confident, he thought that he had discovered everything already in the first attempt, and thought that everything was more or less Morse-Smale, or more or less this kind of Morse, yes, it became known as Morse-Smale flows. So this Morse function, Smale, blah, blah, blah. So he thought that everything was simple like this, because he didn't know the history of dynamical systems. He didn't know even this picture. Someone comes and tells him, look, chaos exists. We found out before. There are these and that examples. There are more examples than that. It's not like always like this. So then what he does, he's kind of annoyed, but then he does better. He understands qualitatively this picture. He goes to Rio de Janeiro, goes to the beach, and as he says, he found the horseshoe there. He found the horseshoe at the beach, like in his mind, which is a picture that describes this. So that he says that everything that's going complicated in this picture comes from a simple drawing that you can do here, which you take a square. So now my dynamical system is discrete. It shrinks in this direction. It stretches in this direction. This would not do much, but then it folds. So it's called a horseshoe for obvious reasons. And you do this map. So the rectangle, tack, tack, and fold. And he says, if you look at the dynamics of this rectangle, you are going to say, to get the complicated things here. So here you have these features that was present on this picture here, that was stretching and so on, and there was this kind of a little bit of folding. And here you get this. So if you take a trajectory here, and nearby trajectory, there will be trajectories that will be going up and down, and they have to do things like this. After you iterate a little piece of trajectory, it kind of contracts, and then stretches, and the stretching kind of combines. I cannot, not very good at drawing, and so on. So he said, and he went further, and using this model, he said, well, that's what happens whenever you have this kind of unstable equilibrium, and then you have this kind of whatever homoclinic point here. So you have this unstable, and you go through an homoclinic point that appears here. So this generates this crossing. As you iterate, it will fold itself into a horseshoe. So it's just a geometric model for what was there. But with the geometric model, he can give a coding, and he can prove theorems about the persistence of the chaos in this. So he showed that there was some kind of persistent chaos associated to that nevertheless could be understood. So next, he gets overly confident again. This works and says everything should be like this. Almost everywhere, this should describe almost everything. Again, it's wrong. He found himself some counterexamples. So actually, most chaos is not stable. So that's what happens. So you cannot describe things in terms of stable chaos. Chaos is there, but it's more complicated than just this chaos that's stable. Like this one was good. He found the model of stable chaos. So you have this picture that he understood. So next, we get to how badly things are with Newhouse, which is the person who understood how those two pictures, this picture can kind of enhance once more this one to get a kind of especially unstable chaos. So now this object here is associated to having a single unstable point, and it's generating all this. Now you can consider this kind of thing, which is a kind of unstable set, which is a fractal set. This will generate a counter set of instability. So actually here, you can imagine that you can enlarge by picking this picture and adding this picture here. So you add enough complications here coming from this here. You add actually a counter set of instabilities here, right? I don't make the pictures here, but imagine that through this counter set, so a lot of points, you can copy this picture here. So you're going to get now, geometrically, through a counter set here, you get all those unstable orbits leaving. So you get a counter lamination emerging from here. And there is through this counter set, there is also things that come to the counter set, right? There is a stable lamination. And they fold and interact. So there will be a picture here that they come here, and then they make some complicated picture. So now the interaction between those two laminations becomes a source of chaos, a more complicated source of chaos. How bad it is? Well, the key here is how stable is the so the points that are generating stability. So Smail showed that if you had a homoclinic point, but the homoclinic point was transverse, it generated some good chaos. Transversality is normally good. He came from differential geometry, so he was used to Whitney and so on. Transverse intersections persist, and that's generated some stability. That's how his argument goes. But in this picture, there are tangencies. So what Newhouse was interested was in understanding how this kind of tangencies could appear in a persistent way between some kind of fractal objects. You understand how tangents appear in this between just two curves, and they unfold to transverse intersection. But what happens here? Can you have some persistent tangencies? So he found out that you can, and it's coded by this geometry here. It's a geometry of the counter set. Here, again, connecting to topology, if you want to try to understand the general picture of manifolds intersecting, what do? So you're allowed to perturb and so on, and try to understand the perturbations. You count dimensions. You look at the dimension of the ambient space, and then you have two manifolds. If the sum of the dimensions is bigger or equal of the ambient space, you may have robust intersection. So there will be a transverse intersection, the generic that you cannot break. If the dimension is small, you can just put them apart. And basically, it becomes the problem of understanding how some fractal objects intersect, but trying to understand how they intersect even after perturbation. It's some kind of transversality for fractal sets. You want to do this transversality theory for fractal sets. Instead of having two manifolds and asking if they intersect or you can break, you now have two counter sets. For some reason, you can project along the laminations and everything happens in the line. So you have two counter sets. So you have a counter set here, and you have another counter set, which for some reason I'm going to use color. And you have another counter set. And you ask if the counter sets intersect. Those are fractal sets. They live in the line. But more than that, you want to know if after you change a little bit the dynamics, what will happen? Are they still intersecting or not? So it's a new theory that's necessary. So it was shown at least some exists. It's still not completely understood, but now so Newhouse gave a criteria for fractal sets to have intersection that persists. So stable intersection of Cantor sets given in terms of the geometry of the two Cantor sets. So he proved that this happened. And he went more. In the end of the 70s, he showed that any time that you get a picture like this, right, so any time that this picture appears at all, and it just appears for the first time an homoclinic bifurcation, so appears this thing that was nice. So the picture since from Newton, it immediately generates this kind of stable intersecting Cantor sets. So these complications that appear here are inevitable once you change from this here. So what theorem this implies? Then he shows that, for instance, forget about conservation laws for the moment, but suppose that you had, for instance, a dissipative system. So area is contracted, right, not preserved. So he can prove that there exists. So there is a theorem that is called Newhouse. In the Newhouse domain, it's the region in parameter space where those Cantor sets stably intersect. In the Newhouse domain, there is the dynamics is extremely complicated, and in fact, he showed that generically you have infinitely many attractors. Attractors are annoying because you expect an attractor that it carries out an open set with this. So you expect that you could, for dissipative dynamics, that you could break your system into finitely many pieces governed by an attractor, but not in the Newhouse domain. They have very tiny basings. They are appearing, disappearing all the time in this infinitely many, but in this whole open set, you kind of keep it. And they are generated by this stably intersecting Cantor set. So he gets this thing saying that, well, as long as things get complicated, they get very complicated. And now many people spend a big part of their lives trying to understand this Newhouse domain. There are many more things. This is just the beginning. That's one of the first Newhouse theorems. But then there are many more complications. So, okay. This looks a little bit complicated, but let's make it a little bit more. All this, I was making pictures in 2 dimensions, except this that was just a manifold. So there was pictures in 2 dimensions, 2 real dimensions. Because I was interested in real systems that arise from this. But mathematicians like to do some other, to generalize and so on. So you can consider what happens for complex dynamical systems, right? So it should be making my life even more difficult to draw. And so what happens when you consider complex dynamical systems? You get some more complicated fractals. Instead of having Cantor sets, you get some sets in the plane. It should correspond. So I will look at dynamical systems in 2 complex dimensions. So imagine that everything that I drew, actually, every curve looks like actually a piece of a Riemann surface that appears here, and everything is living now in situ. And now what corresponded to a Cantor set on the line becomes some kind of complicated set on the plane. And you would have a picture here of sets like this intersecting. So the theorem, so there is a theorem behind the talk that I'm trying to simplify from more. So let me just say that the theorem that we prove with Liouvitch and Zhuang Zhang is that the Newhouse phenomenon, everything that I talked here, holds also in complex. So I'm being a little bit sketchy here because what we prove exactly that is that whenever you have a homoclinic bifurcation in the complex domain, you're still getting the same complications here. All this is excused to show a picture. Let's see what happens in the complex. There is a computer. Okay, so I need a password, I guess. So in the complex, there is a symbolic fractal that dominates. The fractals are not like this Cantor dust. You have a beta fractal, which is there. So that is the famous Mandelbrot set. So that when you look in the plane, in the complex plane, things look much prettier. They look like this. So this is the kind of object that now you're interested in. It's not just some kind of Cantor set which doesn't have a lot of personality. A Cantor set, you just describe a few features. What's the size of the holes and things like this. And then there are concepts that capture a lot, like house of dimension and so on. But here's what you have to worry about. So this is a classical Cantor set, a classical fractal set. Let us look how nice it is when you amplify. This is a particular piece of the Cantor set, of the Mandelbrot set, when you go through the cusp. And let's look at this kind of, what we get. It takes some time to do. It's forming here what look like a sequence of elephants, one after the other. This part of the Mandelbrot set is called the Elephant Valley because of those elephants. And they are just following each other. And a mathematician called Mitsuhiro Shishikura, he investigated this area. And to study the fractal properties of the boundary of the Mandelbrot set, and he proved that the boundary of Mandelbrot set is very complicated. It has dimension 2, the boundary of the Mandelbrot set. And it's because of analyzing those elephants. There are many reasons for that, but that's where he did his work. So look at those elephants, and notice that they have a very nice structured behavior. So because of this structural behavior, this analysis of Shishikura, you find that some Cantor sets that appear when you do this whole analysis, they are very orderly. The elephants look nice, but in fact, there is some order component appearing here. That's just one thing following the other. But there are two dimensions, so it kind of, you get some kind of lattice structure of those Cantor sets. It's difficult to see in the elephant, but it's behind the elephants, you can imagine. So you have Cantor sets that look kind of very orderly. And the basic idea of the proof of this theorem is a new technique to try to show the two sets, they are going to intersect stably. So it's transversality property for fractal sets. But now, what's exploited here is not simply the concept of dimension, which is kind of underlying what's doing this. So concept of dimension, I said dimension of manifolds, that it's house of dimension of fractal sets. You need to have big enough dimension. So you have a concept here of matching Cantor sets. So you have one Cantor set that is generated by something very orderly, like so there is order on one side, and a kind of random Cantor set here. So there are two that appears. On one you see order, and in the other, you see just disorder, normal disorder that appears. That's what you expect from anything, that there will be some disorder. So this is coded into a recent gadget. That's something that's being developed and becoming fashionable, is to study fractal sets by looking at the notion of Fourier dimension of the fractal set. So Fourier dimension means you have a fractal set, you put a measure on the fractal set, and you take the Fourier transform. And if the Fourier transform decays, it means that there is not too much order. It's a way to say that the fractal set is a little bit fuzzy. And somehow, if you match the most orderly of the Cantor sets, the ones that are kind of have a lattice structure, that are appearing for some mysterious reason with through elephants, and they do appear after you do the bifurcation, if you mix this with just like anything that will present some chaotic properties, the conflict between the order of the lattice and this a kind of a disorder measured in this Fourier decay, they will produce exactly what you need to link those two objects for that. The explanation of this use a technique that's called one of the many instances that has renormalization. Here there is renormalization, and this is yet an instance of renormalization. Don't explain what renormalization is, but some tool that allows you to put a microscope here and resolve sets until you detect that they kind of are actually intersecting. Okay, so I tried to make a 1 hour and a half talk in 30 minutes by simplifying a lot. Maybe with questions, it will be
Thank you.
fine.
We maybe only have time for one question. Is there a question from the audience? If not, maybe we should just move on. Yeah. Okay. All right. So let's thank Professor Avila. So thank you, Professor Avila, for a very attracting talk. All right. So our next speaker is Professor